Так, ну что, все, поехали. Okay, hi everyone. Today we'll have a class which will be divided into two parts. First of all, we'll speak about computer vision tasks. We will look through the notebook which we left last time. We'll speak about some more general concepts like weights initialization and transfer learning. And then we'll have about 40 minutes to speak about recommender systems and just look how these the specifics of the task. Да. Sorry, I forgot. Yeah, today we are working in Google Colab since Jupyter Notebook is not installed on this PC. Okay, so let's look through the notebook which we left last time. This is a notebook devoted to classification task for computer vision. The data set is CIFAR 10. It's one of the most conventional data sets used for computer vision. And the task is to classify the images on 10 classes. Here is the list of possible classes. Later, we'll see some examples of images belonging to each of them. So we'll need two libraries. Torch, you're already acquainted with it, and Torch Vision. It's another library from Facebook, which is just devoted to solving computer vision tasks. Well, I don't think we'll have a lot of applications of this library here, but anyway, it's important to know that each computer vision task which is solved using Torch will use Torch Vision as well. So let's inspect this very cell. What is happening here? We just upload the CIFAR 10 data set as an inbuilt data set in Torch Vision, right? This is how we load the train using the option train equal to true. Here, train false, hence we upload the test set. Well, these two arguments, I guess they're obvious, and this one is probably not transform. What does it mean? A transform, we define it here. It's the sequential process of applying different transforms to our data. So by default, Torch Vision CIFAR 10 dataset will upload each image. Okay, so each image is just a set of pixels, and the pixels range is from 0, which corresponds to black pixel, to 255, which corresponds to white pixel. And uploading them with CIFAR, with just this inbuilt data set, will upload them. It will just scale all these pixels by 255. So the range of possible values will now be from 0 to 1. But after we do this procedure, after uploading them in range from 0 to 1, we want to normalize them. And this syntaxis means that, first of all, we subtract 0.5 from each dimension, and then we scale each dimension by 0.5. So that if the previous range of possible values was from 0 to 1, now it will be from -1 to 1. And let's see what's the purpose of such a transform. Why couldn't we just leave the values from 0 to 1? The reason is in weights initialization, and well, it refers to absolutely any deep learning task, that it's very important to carefully initialize the weights. Since if we do not initialize them properly, our network can probably just not converge and will have very low values. I prepared several articles here let's look through the, no, through this one. 1 second, I'll send them to our chat so that all of you can open them. These are 3 articles devoted to weights initialization, and they inspect how the weight should and should not be initialized from different sites. So if any of you knows how, please tell me, how can the weights be initialized in neural networks? Randomly. Okay, and from which diapason randomly? And from? Yes, somewhere around 0, but which one? Just we can use normal, log, uniform, log uniform, and so on. Okay, so let's see different options of initializing, and we'll see how much initialization matters. So this is a good article from 1ZB, and they inspect several options. First of all, they initialize all weights of neural networks to zeros. Just what we see, the result is as follows, that after 20 steps, yeah, the accuracy cannot exceed 0.1. And so probably we'll stuck somewhere around here below the accuracy 10%. For now, we do not know the date, we do not know anything, so it's just difficult to make any assumptions based on this 10%. Probably it's good if the data set has about, I don't know, 1,000 classes, and if it has 10 classes, it's probably not so good.
I'm sorry for being late, maybe I've already covered that. Well, we all know that initializing with constant weights is bad because then the update will be constant, and then all the parameters will be basically the same.
Yes, but your inputs are not the same. So, for instance, you have an image as an input, and across each dimension of this image, the inputs are different. So if we initialize it with zeros, well, like the first pixel for the first image equals 0, and the last pixel equals 1. And so different neurons, while processing them, they will just have different values. And hence
I was just being told that constant initialization gives constant values.
Yeah, it gives very similar values, and if we use just conventional learning rates, like
basically that's why we get accuracy.
Yeah, because well, they just stay in the same range, and they cannot help each other.
For a small learning rate, will have very small different variance in the parameters, so we'll get low quality.
Yes, and in this very example, that's exactly the reason, since all the weights, they initialize to the same values. And secondly, they just, well, it's not secondly, it's firstly, they do not have any variance inside them. And so they all like solve the same task, while the idea of deep learning is to have each neuron solving each probably separate task. So the next way is to initialize all weights to all ones. And well, probably to surprise of some of us, it increases the quality, though we anyway see it's just, its limit is about 25, probably 30% of accuracy. That's better than initializing them with zeros, but anyway, the problem of constant values can be seen here. And now, okay, let's initialize them randomly, as all of you said, but for now, we'll just use a big uniform distribution. So for this very example, we'll have the low boundary equal to -5 and the upper boundary equal to +5. And this is the result. So we already can get on validation, like this line, the dotted one is the validation, the solid one is the train.
So what's the x-axis? Like the x-axis?
The x-axis is the number of training steps. Yeah, the epochs here. Well, I don't know why it was called with step, but anyway, we can see that accuracy increased almost twice compared to the previous time, right? It was about 0.3, now already 0.6. But okay, and for now, let's do the following thing. Let's just tweak the weights more carefully. For now, we initialize them with a just huge uniform distribution. Now let's use some smaller distribution like this very boundary, the lower and the upper one, will be selected more carefully. And this is the example of initializing them with this is from 0 to 1 range. And we already get like 88%. And just these two examples, they can show how much the way you initialize the parameters can matter the final performance of the network. So if we initialize them badly or from some huge distributions, so that some values will be assigned with very big values, our network will just not converge. And if we do it like carefully, like in this case, okay, we get about 88% of accuracy, which is much higher than all the previous ones. This example is the last one when they initialize them with a normal distribution, and we see that the performance is pretty similar to the one we saw on in the previous image, like it's about 88%. So just like, I don't know, like general ideas, we have to initialize them with, first of all, small distributions. Second, we can use some conventional ones like normal distribution in this case, or uniform. Okay, but if we have a lot of layers in a network, if we have a lot of parameters to initialize, if we again use like some standard distributions like standard normal with mean equal to 0 and variance equal to 1, or like uniform from 0 to 1, we'll probably also stuck in some local minima, like we saw it, it was previously, like we saw it here or in two previous images. So when generally we have to, instead of using some standard distributions, we have to make the distributions depend on the number of layers, on the number of neurons in each layer. And this article, I guess, yeah, this is the one. Though I keep on repeating that towards data science is not a very good place to learn something new. This one is a good article, and it also shows the examples of some random initialization of parameters. And there are several good methods which were developed recently during the last 3-5 years, which are shown here. First of all, it's the Hay initialization, which was developed in 2015, like 6 years ago, yeah. And this way of initializing the parameters, it depends on the activation function, which is used after the linear transformation, after the linear layer.
You mean the activation function after the first layer?
We have several layers in a network, and each of them must be initialized corresponding to the activation function, which is applied after it. So, well, yeah, thank you for a question. I just missed one step. Another one article, by the way, it will show the proof of some of the good ways of initializing, like happy initialization. Later, there is a justification of this method here. Generally, the initialization should meet the two conditions, which are listed here. First of all, the mean of the activations should be 0, so that after each layer, the mean of the values is 0, and we will not have some very large or probably some very small values, which will lead to low performance like we saw in the previous article, right? The second condition is that the variance of the activations must be constant, across all the layers of the network. Why this should be, this condition should be met? Because if the variance on different layers will be different, well, since we initialize them randomly, probably some values on, I don't know, layer number y will be very high. And after they will be applied by the values of the next layer, they will lead to very high or probably vice versa, very low values, which will lead to very huge gradients. And huge gradients, they are one of the reasons of overfitting, or not overfitting, of underfitting, when the model is stuck in some minima and cannot just get out of there. So these two conditions must be met, and several techniques were invented. This is the initialization. It uses the normal distribution with mean value equal to 0, and this is the value of standard deviation. And in this article, this one, where the authors proposed this method, they proved that when the activation function is ReLU, this way of initializing the values will meet the following condition and will lead to the most beneficial results for the network. There is also another one very popular way of initializing the parameters, which is often asked on different interviews and so on. It's Harvey initialization, and it's sometimes referred to as Glorot normal or Glorot uniform, which depends on the distribution we use. Here we can see this is again the random normal distribution, but the standard deviation is slightly different. Now it's just 1 divided by the size of the previous layer, in comparison to initialization, where we saw it was just 2 divided by the size. By the way, the size L minus 1 means the number of neurons in the previous layer. Okay, so Harvey initialization, it was shown that it's the most beneficial for the network when the activation function equals to hyperbolic tangent with possible range of values equal to from -1 to 1. I hope everyone remembers. Yeah. And this is another just good way of initializing the parameters, but in Torch, there is just the third way. And now we will just inspect it. In case you forgot, you can just type Torch linear and it will be listed here. So they use uniform distribution. Yeah, 1 second. Instead of the normal one. And these are the boundaries, while the K is 1 divided by number of features, just in features, which is the number of hidden units in the previous layer. Okay, so basically it's just very similar to what we saw here, right? But here it was the standard deviation of the normal distribution, while in Torch, this is the lower and the upper boundary of the uniform distribution from which the weights are just initialized. Yeah, that was a question.
What's the default initialization in Torch?
This one. You can see they are initialized from uniform with such a boundary. And just using this formula, we'll have the mean value of 0 after each activation, and we'll have the constant variance across all the layers, which will lead to the maximum performance of a network. Okay.
Assume that the distribution of weights is the same for all layers.
Distribution. I mean that it's the same across all the layers.
Yes.
But it's not the same. So we have different number of hidden units in different layers usually, right? So for instance, we have just the example we saw on the second seminar, we had the about 300 probably input features. I don't remember exactly the numbers, but about 15 hidden units on the next layer and 1 in the last one. So all of them will be initialized with different distributions, since the K will be different across the layers. And well, in this case, that's okay, because, well, anyway, even if the number of hidden units is the same across all the layers, they are sampled randomly and will not see just the repeated values among them. That's it. Okay, so this is the reason why we transformed it here, so that the range of possible values is from -1 to 1, and just with such the initialization, this is the best way of transforming the images, to have them in the range, the pixels in the range from -1 to 1. Here is a small example how we can just visualize a couple of images. We can use again Tsvigun utils here and make read function to visualize them. We can see these are the 4 example images: plane, bird, cat, car, cat. Yeah. So let's move on to our network. And as we discussed it previous time, in computer vision, the most important layers for feature extraction are the convolutional layers and the max pooling layers. What we do, this part refers to feature extraction. We apply convolution to our data, then we apply the activation function, then we apply the pooling. On the next layer, again, we apply the convolution, we apply the ReLU, and we apply the max pooling. Max pooling is here with filter size 2 by 2 and stride equal to 2, which means that after this and this step, the dimension of the image across just width and height will be shrinked twice, since the stride equals to 2. In addition, we can see that convolutional layers, and it's it happens all the time in computer vision networks, it increases the number of channels. So the first argument refers to filter size, and the second refers to number of channels. And as an input, we have a colored image, which means it has 3 input channels. Yeah, just red, green, and blue. Here we multiply it twice to transform it to 6 input channels, and here we just transform it to 16 input channels. The purpose is as follows: that we can find some intersection of features among all, just across different input channels, which will show some most important qualities of features for a network that it can classify it very well. Okay, after this very step, the feature extraction part is over. We flatten our input so that it can be passed to the linear layer next. We saw last time that to use dense layers for convolutional networks, we need to first of all flatten them, so each image will be presented as a one-dimensional vector after this operation. Then we apply the classification part. We use 3 linear layers with 2 activation functions. Just first layer ReLU, second layer ReLU, and the last layer. By the way, this is how to back. Yeah, this is the peculiarity of Torch, that when you build your network, you do not need to use the final activation in the end. So, for instance, here is the classification, the multi-class classification task, and the activation function which needs to be applied in the end is great. Everyone knows.
You have some problem in this layer. I mean, you have self.text. You should have self.text1.
Yeah, thank you. So in Torch, the final activation, it is just inbuilt in the loss functions. So in the next cell, we say that the loss function will be cross entropy loss. And if we examine this very function, I do not have this notebook just running for now, so I cannot use Shift Tab. But what we can do, we can again Google it here, and it will say that it combines the cross entropy loss and the logs of max. The logs of max and the NLLL loss. This is probably just not very easy for everyone. The reason is that cross entropy loss is multiplying the true label by the logarithm of probability of the predicted value, right? So it's the same as applying, first of all, the logarithm for our predictions, and then applying the negative log likelihood loss, which is just what cross-entropy loss is consists of. So all the inbuilt losses in Torch, like the same as for binary cross-entropy, they combine the activation function and the loss function together. And if we use the softmax function here additionally, like x equal to softmax from x, it will mean like while calculating the loss, we'll have the softmax function applied twice. So first of all, it will be here, and then it will be while calculating the loss, which will lead to some bad results. And it's very important not to forget about this, because well, it will lead to some very poor performance, and it will be difficult to understand why. For optimizing, we'll use the just classic stochastic gradient descent with some predefined parameters here. But well, we could use the Adam, and probably it would lead to some better results. Yeah, sure. Yeah, the conventional way is to increase them always twice. I don't know why they use 16 instead of 12, but well, anyway, if you increase them 3 times, I don't think it will very much differ the performance. Just
want to increase to the number that will give us quite enough information.
yes, that yeah, we shrink the dimensions across width and height, right? But instead we increase this dimension across input channels so that we preserve this very information.
You mean how you can, at the end of the day, you can just put it as a hyperparameter? Well, okay, as a parameter of the network.
Yes, using the validation sample, we can tune it for sure, but the number of input channels will not so much differ it.
Well, I'm just not sure for some more complex networks where they have like 3-dimensional convolutions, one after another, well, that might be the case. But well, I doubt that for image classification. I agree that that would be an overkill to say.
Yes, but for large neural networks, it will be very hard to tune the hyperparameters, since just building another one from scratch will require a lot of time. But anyway, that's a good point. So here is the train loop. It's just similar to the one we used for our first neural network, but it just doesn't have any, I don't know, steps like we used to output the data frame and so on. It's just, first of all, we extract the batch. I don't know why it's called the data here. Probably it would be a better idea to call it with batch. So it's just the same as it was in our data set. Like the data set outputs for the given index a tuple of 2 values. The first value is the inputs, the second is the labels. Yeah. The order of 0 grad here is slightly different. The 0 grad just at first, while just in our network we used this line. It was, oops, it was. Huh?
It doesn't matter.
It doesn't matter. Yes, after each step, we'll just zero the gradient and everything will be okay. So we pass our values to our network. We calculate the loss. We calculate the gradients, and we do the optimization step. After each epoch, after each 2000 step, we output the loss value, and we can see that it gradually decreases. So, well, probably, not probably, for sure, it would be a good idea to train this network for several more epochs, like 10 or 20 epochs, and we'll get some better results. But the purpose here is not to just achieve the maximum performance. The point is just to see how all of this works. When we finish the train of our network, the best idea is to save it so that we can use it later. And in Torch, the networks are saved using their state dicts. So the state dict is the dictionary which contains all the parameters of the networks. They are named. And so after we initialize our network and load this very state dict, we will get the same network. So Torch cannot, well, it can, but it's not the best way to save it as a whole network, but usually it's saved just using the state dict. When we want to load our network from this very path, right, we just need to do load state dict and provide the path from which we want to load this very dict. Here are the 4 example images. We can see the cat, sheep, plane. Yeah, we make the predictions for them using this very network, and what we get is cat, truck, car, plane. So 2 of them were classified correctly, and 2 ships were not classified very well. Though anyway, it just mixed up the ship not with cat, but with truck or with car, which are probably similar to the ships. Here is the evaluation loop. We evaluate our model on the test set, and we see that the total accuracy across all of the 10 classes for 10,000 arbitrary images is 56%. So our network is at least significantly better than the random predictions, right? So we can see it has learned something at least. And the next cell, it just shows how we can estimate, how we can measure the accuracy or any arbitrary metric for each class, a good cell. And we can see that surprisingly, the ship is classified, just has the best accuracy across all the classes, while in our example, we had 2 errors for the ships. Well, that's just interesting. Okay, so any questions for code? Some difficult places, because the first homework will be devoted to computer vision networks, and you'll have to probably use this the information from this notebook. Okay. The next point, we need to just here they say how we can increase the performance of network, and the second point, we see train a state-of-the-art ResNet network on ImageNet. What does it refer to? So ResNet is the architecture which has about, if my memory serves me right, 30 layers or probably more. It has several million of parameters, and of course, it would be impossible to train such a network from scratch using Google Colab or using any just small computational.
You mean exactly this ResNet, or which I mean original ResNet is not the like evolution of a network, like there is ResNet.
The pre-trained model.
Yes.
Yeah, I mean some concrete example. Yeah, I mean какая-то конкретная сеть. Ну, это ResNet, что
Большой просто, ты просто так не можешь взять сразу.
просто ResNet бывают разные, то есть как бы я могу.
Давай на русском. ResNet бывают разными, ты можешь менять число слоев, можешь менять число параметров. ResNet обычно относится, когда говорят, ну то есть с нуля, на самом деле, ты ResNet никогда не обучишь, потому что если ты используешь мало слоев, он тебе никакого особого перформанса хорошего не даст. А если будешь использовать много слоев, ты ее будешь до бесконечности обучать, потому что она обучалась изначально, она, по-моему, 20 ГПУ сразу, ну вот вместе. Но это только там большие компании себе могут позволить. ResNet, по-моему, 2 недели, если я правильно помню. Она еще не самая большая. Большие модели еще больше. Okay, so the general idea of and why all the computer vision or we'll later see the natural language processing technology, why they just received such a prominent boost, like, I don't know, Face ID on your telephones, it can very well classify you from somebody else. Or probably like Tesla machines, they can segment and classify all of the instances which it sees. And just how do they do all of this? Why this significant boost took place recently? The reason is into general methods. They refer to as transfer learning and fine-tuning. I will show the images in our Telegram chat since it cannot be uploaded here. Probably I will be able to open them somehow. Нет, сегодня будут. Сейчас мы уже приблизимся к концу с компьютер Vision. Будет рекомендательная система, но мне нужны эти фотки, которые не открываются на коллабе у нас. Okay. So there are two general concepts which I applied just across all of the spheres of machine learning, and they're transfer learning and fine-tuning. This is the first image. So the traditional machine learning, we have a task. For instance, we have to classify, I don't know, 5 objects like, okay, let them be animals like cats, dogs, cows, and 2 more types of animals. What we generally do, we have this data set. We just learn our model on this very data set from scratch, and we get some probably good results. And the just more advanced idea is the transfer learning. And this is as follows. Instead, just we can mimic the logic of image while learning the networks. So when we just are assigned a task to classify something which we have never seen previously. For instance, we will take some medical drugs or molecules, or how is it pronounced in English? Some images of molecules, and we'll need to classify them. Of course, none of us will just achieve good performance since we have never seen such tasks before. But if we are given the images of cats, cows, and dogs, and we'll be asked to classify them, of course, we'll have the accuracy close to 1, since we know where is the cat, where is the cow, and so on. And the same idea can be applied to deep learning, to neural networks. What we can do is we can first of all train a network on a very large data set. We can use just several million of images or several dozens of millions and train a very large network, which will be a good feature extractor. And as the next step, we will take this image, we will slightly modify it, and then we will be able to apply it to one task. So the pre-trained network, I mean the pre-trained on such a very large data set, it will be a very good feature extractor. So it can very well achieve good latent representations of all the images, right? And then when we just add several new layers and train them, these layers will help us classify and get just the results for the target task. This is the idea of transfer learning, and this is not just, okay, the transfer learning is this very idea that we can train our network on some very huge amount of data, a very big neural network, and then we can apply it for some different tasks. And just how to do this, we refer to as fine-tuning. Fine-tuning means we take a large pre-trained network and we slightly modify it to make it applicable for our very task. So let's see the example of this here. So we use a very large data set, for instance, ImageNet. ImageNet is a data set consisting of several millions of images. We pre-train a very large network here. We have some personal loss here. How to choose the loss when pre-training on large data sets. For instance, ImageNet is just the data set which consists of several millions of images. And assigning a label for each image would be, I guess, a very hard task, right? So What we do, we need to find such a, we need to make the so-called self-learning. So the process of labeling the images, the process of labeling the instances will be inbuilt in this data set. For instance, what can we do? We can corrupt our images. We can, I don't know, like divide it into 9 parts, then mix up all the parts. And as we know which parts were correct, we need to just ask our models to restore the original image. So it has like, each image will be presented as 9 blocks. And what we need to do, we need to sort them in the correct order so that the image will be restored. And this does not require us to make any labeling of our data set. So we can just download a large number of images and make this process of self-learning. So we will randomly corrupt each image and ask the model to restore it. And after pre-training on such a large amount of data with a task which is similar for just the tasks which person solves to learn which image, just what is situated on the image, this network will be a perfect feature extractor, so it will have a very good latent representation of each image. Now, what we do next, since in previous task our goal was to restore the original image, probably some last layers and the loss function will be different from the one which we need for our very task. So what we do, we just cut these very layers, we add just 2 or 3 more layers here. Here it is called the shallow classifier. It can be any just 2 or 3 dense layers with activation functions between them. And we just have this part as a very good feature extractor, and all we need to do is just to fit this very small classifier part which we added here.
And I'm sorry, on the second step, we update only the new layers while training. I mean,
here.
Yeah, here.
Yes.
We do not like update the first.
Yeah, that's a very good question. Conventionally, it's deemed that we need to freeze all of these layers since they are just feature extract and train only these layers. But in practice, it turns out that sometimes this is not important. And in some cases, if we only train the classifier without training the rest of the network as well, it will lead to significantly lower performance than when we train the full network. So the best idea is as follows. Since this new layers, the classifier of our network, it was just, we added some new layers which were initialized randomly. If we now make the back propagation from this very step, the layers which contain some information about our image, about just general images, they will be backpropped with respect to some layers which were initialized from random distribution. So this will lead to corrupting the information contained in these layers, and this just the idea of transfer learning will probably fall. So what it's believed the best way, first of all, we need to freeze all of these layers. So on each backprop step, we do not update their weights. We train only this part for some number of epochs, I don't know, 1, 2, 3 epochs. And after it has just converged to good values, then we unfreeze these very layers and we train the whole network from just not from scratch, but from this very moment. We train the whole network, we update all the weights, and this will lead to the maximum performance. That's it. So what is done in, for instance, computer vision? There are several very large pre-trained networks like ResNet, like AlexNet, like VGG. And when we have some task which has low amount of data, like, I don't know, you have only 1,000 or several thousands of images, which is insufficient to train a network from scratch, but it's all right to use the pre-trained network, add some layers to it, and train it the way we've discussed just now, so that the model will fine-tune for this very data set. And that's what fine-tuning is. I don't know whether it was too difficult or not, but if there are any questions, please ask me. You're just so funny. Okay. So if there are no questions, if this is obvious for anyone, let's move on to recommend the systems. We have about 30 minutes more. If we take about 5 more minutes of break, we'll have 35 minutes. Okay, so let's first of all speak about some general concepts of recommender system tasks, because recommender systems is just another direction in machine learning, which is not similar to computer vision. It's not similar to natural language processing. It's not similar to speech recognition. It's just a separate field of machine learning. And well, I can say, for instance, in our laboratory of artificial intelligence, we have just a separate group which solves the task of recommender systems. So what's the specific of the task? First of all, it's the data and how it looks like. The general way of having the data for recommender system is as follows. We have some users, we have some items, and we know in which way each user interacted with each other item. So for instance, for this very data set, this is the table with the interactions, and it says the person with this idea interacted with the content with this idea, and the just interaction type was as follows. For instance, here it was the view, here it was the follow, and so on. By the way, the data set is the real data which was collected during 1 year from some platform, which collected the data from people reading some articles they could just read, like, comment, follow, and bookmark the article. And we have this very data, and we need to recommend new articles to some other users. So based on the history of their interactions, we need to recommend some items to them. In addition, for the majority of tasks, we have some features. First of all, for content. Second, for people. For instance, here, for content, we have these very features. We have the URL of it, we have the title of it, and we have the text of it. When we deal with some just more general applications of recommender systems, for instance, Spotify, Yandex Music, Boom, just referring to music, or probably Okko, or I don't know, any like Netflix video services which are applied to films. We have some additional features for each item. Just let's say about music, we have a song, we have the author of the song, we have the genre of the song, and we have the probably date of recording of the song. Well, if we know that the song was recorded in 1970, the probability of that it refers to hip hop, for instance, is very low. And based on that, we can assume that, for instance, for young generation, it's not the best idea to recommend songs which were published in 1970. And we need to somehow just concatenate all this data, use all of this to get the maximum performance for recommending new items to our users. So let's quickly look through some very simple, but some of them yet effective ways of recommendations, and then we will just go next to autoencoders. First of all, we will recall which types of autoencoders exist, and then we'll see how they can be applied to recommender systems. So for this very task, we do the following thing. I have 5 types of events, and since we need to build the user item interaction metrics, we'll speak about it a bit later, we need to somehow encode all of these event types. We use the following mapping. So just when the person comments the material, it means he was just, I don't know, excited about it, and it gets the biggest value, while just viewing gets the lowest value. Yeah. So the most primitive methods. The just the most simple way of recommendation is just recommend each user the most popular items among all of the data set. So, well, generally it will lead to some not so bad performance, since if we recommend the most popular items, it's obvious that for some people who are just whose preferences are, I don't know, general, with some common preferences, they will like this content and we will guess correctly. So here we build I will not deepen into this code. It was taken from Kaggle notebook. The idea is just to show how each of the methods performs. So yeah, the metrics for recommender systems have not discussed. Some of the general metrics are recall, I don't know how this symbol is pronounced, recall 5, precision 5, precision 10. Just generally these metrics are called recall n or precision n, and they are as follows. It was somewhere described here. Yeah. So what is recall n? To get the value of this metric, we need to do the following thing. We need to take the item with which the user interacted, and we know them. And we also need to take 100, for instance, for this case, or sometimes 1,000 other items with which the user has not interacted. We need to make a recommendation for these very 101 items, and recall n will measure whether this very item with which he indeed interacted is present in these n top recommendations. So for instance, recall 10. What we do, we take the item with which the user has interacted, we take 100 random items with which the user has not interacted, we make the predictions for these 101 items for our user, and we take the 10 most confident predictions. And if the item with which he interacted is present in these top n predictions, then we get +1 for this just value. If not, we do not get anything for this. Okay. There are some other ranking metrics, NDCG, MapN, and so on, but well, they are slightly more difficult. Will not deepen into them, but here is the link to the post where it's described perfectly in case you get excited about this. So for this task, we'll measure two metrics, recall 5, recall 10. And the popularity model, which recommends the most popular items for each of the users. So we must understand that for each user, the predictions will be just almost the same, that only the most popular items with which he has not interacted before will be recommended to them. And here is, was it really these very metrics? Okay, so these are the metrics for it. So generally, well, when making the procedure which we just have described, the probability that the item with which he has indeed interacted, the probability that it will belong to 10 most confident predictions is 37% for such a model, not the worst recommendation, right? So it shows some good performance, I can say. Okay, so the next model is the content-based filtering model, and the content-based model uses just the features of each item, or probably of each user if we build it in a transposed way, but let's speak about this later. So the content-based filtering model, it just uses the features of each item, and we know with which items the user has interacted, and we recommend to him the most just close items to the ones with which he has interacted. For this very task, we saw that we have the text of the article and the name of the article. It was here. What we can do is we can use some feature extractor from this text information, and we'll have some features for each text. By the way, does anyone know how to extract features from such textual information? for now without deep learning. Just Oleg.
Well, just please remove some stop words, remove punctuation.
Yes, and how to extract the features. You say about just describe how we can remove the noise.
Well, then we just get some sort of, well,
I mean, how to encode the text or how
Yeah,
to,
how to encode the text.
like word to text or
well, it depends on the model that you would like to apply. You have encoding, well, there's many types of encodings and embeddings you can apply. But it depends on the model that you apply.
Well, here what we want to do, we want to use a simple like logistic regression, or which will show whether the two items are similar or not. But
This TF-IDF.
yes, for this very task, the TF-IDF will be the best way, and it will produce the maximum quality. Does anyone remember how TF-IDF works or not? Yeah, that's the bag of words and TF-IDF. Okay, so for now we can just remember TF-IDF calculates some metrics for each word in each text, and in our next seminar we'll slightly deepen into TF-IDF when we'll refer to textual methods for deep learning. Yeah, so we can apply TF-IDF. We'll get the features vector for each item, and we will be able to find the similar items for each of those the user has interacted with. Let's get back. And this model will be referred to as content-based filtering model, since it's just based on the features of the content. And building this model and evaluating this will receive these very results of metrics. So we can see that such a model is even slightly worse than the population-based model, right? For population-based, we had about 37% here, 24% here, while for content-based model, I have lost it. It just goes back. The metric size follows, which means that, well, the popularity-based model for such a task is even better, though we must understand that popularity-based model is just not machine learning, is nothing, it's just the most primitive way of recommending the items to our users. And now let's move on to collaborative filtering model. And collaborative filtering models are the best ones in recommender systems. They are used in all recommender system tasks, and collaborative filtering models, they deal with user item interaction matrices. What does it mean? So previously we had our data, you remember it was just a data frame where each row just told us which user with which item in which way he interacted. Yeah, and now what we do, we like build the pivot table here. The rows will be the different people, and the columns will be different items. And for just on the interactions, we have the value with how the person interacted with this item. Of course, this matrix will be very sparse because a user generally interacts with a very small amount of items. So more than 99% of values for this matrix will be zeros. But anyway, what can we do? We can just use some basic methods like singular value decomposition, for instance, to get the vector representing each person and the vector representing each item. And then we'll multiply the vector representing a user by the vector representing the item. And after multiplication, if the value is big, then it means that this the user and the item matches very well, while when this value is small, it means they do not match very well. And SVD has been considered the best way for recommender systems till 2015, when the first autoencoders appeared. Here is the example of using the SVD decomposition for such a task. And in the end, we get the following quality. We see that it's significantly larger than the previous metrics for popularity or content-based model, which means that it's just a very good recommender system already. But let's move on and let's build the hybrid recommender system, which will use both the user item interaction metrics, like the collaborative filtering model did, and it will use the features of each item as well. So it will be both collaborative filtering and content-based. And just combining these two methods, we get a slight increase in these metrics in comparison to the collaborative filtering model. So not so prominent, like 46.8 here and 47.9 here. But anyway, we can see the boost even after this just naive blending of the results. And now let's move on to autoencoders, the most interesting for us part. But before we move on, let's recall which types of autoencoders exist. If some of you watched the course, it was in week 4.
Also variational autoencoders.
Yes, the first one. Any other?
Well, in real life, no one actually uses, in the majority of cases, except, well, okay, the majority of people use autoencoders or variational autoencoders as well.
Yes, and there is the third important type. Okay, so in your course, if some of you watched it, it was also spoken about like contrastive autoencoders, sparse autoencoders, which are very rarely used in real life. In real life, there are 3 most important types of autoencoders. The first one is just classic autoencoders. They do the following thing. Like, for instance, for this very matrix, which we saw here, we have a lot of different items, about 3,000, and we have more than 1,000 rows. What it does, it just gets this matrix as an input. So we can assume that each row, each instance has about 3,000 features, right? What it does, it decreases this vector to a smaller dimension, because that's obvious that if we want to represent each user with a vector, we do not need 3,000 values. We can probably deal with some significantly less amount, like 300 values or probably 100 values. And when we decrease to this very dimension, we will preserve only the most important information. But if we do not do the next step, we'll lose this information. So what we need to what basic autoencoders do, they first of all decrease the data to a smaller dimension, and then they increase it back, they restore the original dimension, so that we urge our model to contain only the most important features for each row. So it gets for each person, it has an input of 3,000 features. It decreases it to 300, for instance, and then it restores it back to original dimension. And after we do this operation and ask our model to restore the original matrix, what will happen inside the neural network? It will try to preserve only the most important information, which is necessary to restoring the original vector back. That's it. So these are the general autoencoders. The ones which Tsvigun told us about variational autoencoders, they refer to Bayesian modification of autoencoders. So instead of doing only this procedure described, we can, instead of urging our model to output the same input matrix, we can urge it to output the distribution of values for each original value of the matrix. When we ask it to output the distribution instead of the concrete value, it will show significantly better results, since like in real life, when a person is asked something, it's difficult to just guess the answer exactly, but it's significantly more easier to guess the distribution where the answer can stay.
What if variational autoencoders then better for the kind of system? So we have like a prime distribution would be some sort of set of parameters of the user that we got, for example, age, country,
yes, the benefit of using variational autoencoders for neural networks is in that it's when we decrease the dimension, it's sometimes difficult to restore it back, since we used to we contain information in 3,000 features, and now we need to restore it from 300 features. But when we output the distribution in this case, it performs better, since we do not urge it to output the exact values, but we only need to get the distribution where this value can stay. That's it. And there is also the third very important type of autoencoders, which is applied for computer vision. For now, it's one of the most prospective spheres, I can say. These are the denoising autoencoders. So for instance, we have an old film, like, I don't know, from the beginning of the previous century, and for sure it will be of poor quality. What we need to do, we need to have it in a better quality. And how can we do this? We can take the films which were recorded recently, like during the last decade, and we can apply, we can add some noise to all these films, or we can probably make them black and white, all the modern films. And after having this film in black and white as an input, we can ask our model to try to apply such transformations that the output will be the real film, just colored one. And when we train our model on a lot of films, so that it has an input as a black and white film, and we ask it to output the real film, we can then apply it to all the films, and then it will just learn how to transform the films from 20th century to make them of better quality and probably to make them color. So that's the idea of denoising autoencoders. For these autoencoders, it's important, we sometimes do not decrease the dimension. So the input was like of an image, I don't know, 500 by 500. And in the intermediate layers, we do not decrease the dimension, not to preserve any, not to lose any information here. Today, we'll have a look at the just classic autoencoders, the one which was suggested in article Autorec in 2015. It looks just, you can see by the way here, while building this notebook, I used this very just magic line with load. So all of this is, I have it written in some Py files, and what I need to do to get this cell without writing all of this from scratch, I just need to run the cell, for instance, or for sure, for now, it will not produce any results since we are on Google Colab, not on my local computer, but anyway, I hope you all remember this. So what we need to do, we need to get our user item interaction matrix from, again, from our just original matrix. And we need to apply some small autoencoder to it. So probably we'll get some better results. But here I use the hidden size of 500 to just preserve as much information as possible, because, well, increasing this value will not have any boost, but 500 for this very task is, I found it the best one. It's just the most primitive autoencoder. So we have first layer transforming it to hidden size, yeah, one ReLU transformation, and then we restore it back so to 300 features. And what we the task of our model is to restore the original matrix. So we have this matrix as an input, we decrease the dimension, and then we ask it to restore. What is important for recommender system task is that we can use some conventional loss functions like MSE or RMSE here, but it's important to remember that we need to calculate it only for values which were non-zero, because the majority of values, more than 99.9% of values of this matrix, will be zeros. And this refers to the absence of interaction. And it's very important that when we calculate the loss, we do not include these values with just absence of interaction. So here is a small modification for it, so that we use the mask and we calculate the loss only for non-zero values. Then we train our model for I don't remember, like 100 epochs here. We get some quality. We build the same like predictor here, and the results is as follows. So recall 10 is significantly larger than we saw previously, but interestingly, recall 5 is not so great. So the comparison of methods looks like this. So autoencoder has the best recall 10, but it does not have the best recall 5. Why does this happen? Because we had, as our model, as our autoencoder, we had only one hidden layer. It was just a single layer perceptron. And it could not, first of all, it could not keep enough information just containing in our user interaction matrix. And first of all, it did not have very much just nonlinearity, since we applied it only once. We had only one rule transformation, and it will be just close to a linear model, since there was only one non-linear transformation. So generally, it can guess the trend very well, like here. So if we take the 10 most confident predictions, the true interaction will, with probability more than 50%, will be contained there. But the probability of that it will be contained among top 5 predictions is significantly less, yeah, because probably it do not have enough parameters, our network, to encode all the information to just make the target contained in the top 5 values. That's it. And that's the general just case with autoencoders, that sometimes using recall n with small values like recall 3 or recall 1 or recall 5, it shows just poor performance comparing to some collaborative filtering methods like SVD. But if we use some bigger values like recall 10, it will show some good boost, as we can see it here. So we even have not used your break. That's all for recommender systems for today. If you have any questions, please feel free to ask them.
What is the point of inception score and how it is different from other quality metrics?
Inception score?
Yeah, I think it's quality metric from computer vision.
Inception is a pre-trained model for computer vision tasks. You can check it out.
Remember seeing like inception score?
Inception, right?
Let me just double check it. There's an objective metric for evaluating the quality of generated images. What's sort of more from the generative models than from computer vision, but it's more in still computer vision. Okay, there is some. I just didn't really get it. What was the point and how it is different from?
Well, to be honest, I do not remember by name the inception metric, but I can say that for generative neural networks, the loss functions and the metrics which can very well describe their performance are some metrics which are based on the similarity of distribution. So for instance, like L divergence, we can see how much our image, our generated image is close to the distributions of images where we want it to stay. There it is. Okay, so that's all for today. Thank you. Yeah, on our two organization news, ну, уже можно, наверное, на русском. Во-первых, сегодня, либо самый крайний срок завтра с утра, я выдам домашнее задание. Оно будет по компьютерным сеткам. Оно будет на 2 недели. Да. И, скорее всего, через 2 недели у нас будет конец этого курса. И пока, ну, то есть вот нашей части, у вас начнется сам курс по NLP. И через 2 недели я как раз оформлю ДЗ. Оно будет, скорее всего, на выбор либо по NLP, либо по рекомендашкам. То есть кому что интересно. По NLP, скорее всего, мы его оформим на Кегле. То есть, чтобы там не было каких проблем, у нас будет датасет, нужно получить наибольшее качество, можно использовать все, что хотите. Вторая организационная новость, пока еще все не ушли. Нам в следующий раз тоже пишем работу, как в предыдущий раз. И опять же, завтра, скорее всего, я скину список вопросов, по которым можно будет подготовиться. Среда не в субботу стоит? Но я устрою опрос, но, по-моему, в расписании на субботу стоит. Да, в тот раз, кстати, было довольно много случаев списывания. Вот. Я, конечно, не хочу там что-то называть по именам, говорить и так далее, но правда было много. Вот, поэтому квиз лучше будет написать очно, потому что так мы это дело сократим.